and welcome to lecture 55 of analog integrated circuit design. In the previous lecture, we discussed the band gap reference in great detail. It provides a very stable voltage reference that is independent of process variations and temperature. It gives you 0 temperature coefficient at a particular temperature, so that the voltage variation over the temperature range we are interested in, that is about 0 to 100 degree C, is small enough. Okay. In this lecture, we will look at a slight modification of the band gap reference that enables us to design it for low supply voltages, and then go on to voltage regulators, which are another crucial parts of biasing circuits. They provide supplies for other circuits. The band gap reference that we had was like this. Perhaps I will show it with transistors, PNP transistors, which is the common thing to use in a CMOS process. And this is the output. If everything has been designed correctly, this output, which is VB1 plus Vt log n times R1 by R. If this has an area of 1, this has an area of n, equals Eg naught by Q, okay, and this is independent of temperature. And we know that this is 1.2 volts. So, the minimum supply voltage with which this circuit can operate is the voltage that appears here, which is 1.2 volts, plus the voltage required across M2 to keep it in saturation region, okay. And typically we need about 200 millivolts across a transistor. So, the lowest supply voltage is about 1.4 volts, okay. Now, this is all right if you have supplies higher than this, let us say 1.5 volts or higher, but these days you have to operate many circuits with a far lower supply voltage, such as 1 volt or 1.2 volts. So, this circuit cannot really be made, but we can slightly modify this circuit, so that we can get a temperature independent reference with a smaller supply voltage. Of course, we cannot get a 1.2 volt output voltage from a smaller supply voltage, but instead of 1.2 volts we get a fraction of it, which is also temperature independent. It will be just fine, okay. Now, if we go back to the evolution of the band gap, what we did was we had the PTAT cell in this, VB1 is available in these two places and this is VB2, and to add PTAT voltage to this, we recognize that the currents in these two branches are proportional to absolute temperature and add a resistance in series, okay. So, this is R and that is R1. So, if we place this resistor in this branch, we get VBE1 plus a P TAT voltage and the final output is the band gap voltage. Okay. Now, so all we have to do is to add VBE to this P TAT voltage. Okay. Now, this can be equally well done in the current domain. Okay. First, now we recognize that in this particular circuit, currents in M12 are proportional to absolute temperature. They are equal to Vt log n divided by R. Okay. So, instead of adding voltages, that is instead of adding VBE to a voltage that is proportional to absolute temperature, we can take the current that is proportional to absolute temperature and add a current which is proportional to VBE1. Okay. So, we know that the voltage here and there are both VBE1. So, if we add the same resistor R to the two sides of the circuit, what happens is the currents in these will be VBE1 by R, both of them. Okay. The currents in M1 and M2 will still be equal to each other, but they will consist of the proportional to absolute temperature which are flowing in these bipolar transistors plus this current which is proportional to VBE1 flowing in the resistors. Okay. So, in this particular circuit, currents in M12 are the sum of P TAT current and let me use a different symbol for this, R2, P TAT current and a current that is proportional to VBE1. Okay. And we can write this as VBE1 plus Vt log n times R2 by R divided by R2. Okay. You see that the numerator is of the same form as before, it is a voltage which is the sum of a base emitter voltage drop and a proportional to absolute temperature voltage drop. Okay. By adjusting the ratio R2 by R, we can make this temperature independent, that is make it equal to the extrapolated band gap voltage Eg naught by Q. Okay. So, the current in this will be then independent of temperature and we can replicate this current and pass it through a resistor to get a voltage that is independent of temperature. Okay. So, what we then do is have a resistance R3 over here and the current in this, if I call this M3, ID3 is VBE1 plus Vt log n R2 by R divided by R2 and therefore, the output voltage is this times R3. Okay. So, if this R2 by R is adjusted correctly, the term in brackets will be the extrapolated band gap voltage Eg naught by Q. Okay. And if we set this R3 by R2 ratio to be smaller than 1, what we get here will be a fraction of the band gap voltage. Okay. For instance, we can set R3 by R2 to be let us say half, then the voltage that we get here is 0.6. Now, everywhere in the circuit here you have VBE which is about 0.7 volts, Here also it is the same, it is about 0.7 volts, and here it is 0.6 volts. Okay. So, the minimum voltage that is required, which was the main point of modifying the circuit, is VBE1 plus VD sat M1, which is approximately 0.7 plus 0.2 volts, which is 0.9 volts. Okay. Whereas earlier we needed 1.4 volts minimum supply to build our band gap circuit, now we need only 0.9 volts. Okay. This circuit, which was basically an adaptation of the original band gap circuit in order to operate with a low voltage, is called a fractional band gap circuit. Okay. The principle is very simple. Instead of adding the base emitter voltage and the proportional to absolute temperature voltage in the voltage domain, you add them in the current domain. Okay. And this circuit is called a fractional band gap reference. Now, this circuit is also self biased like our circuits which generated currents for constant GM and so on. So, this will also need a startup circuit, and the principle is exactly the same. You can look at the node at which the voltage should be VBE1. If it happens to be 0, you can pull some extra current from the some points in the circuit, which will enable the circuit to start up. Okay. And as usual, you should make the startup circuit weak enough, so that once the circuit is started up, the startup circuit drops out of the picture. Okay. Now, a couple of more points about the band gap, whether we take the fractional band gap or the regular one. Let me take this one for now. As with the proportional to absolute temperature cell, M1 and M2 have different values of VDS, the drain source voltage. Okay. So, this means that the currents in M1 and M2 will be different. Okay. Now, this will cause some errors in the band gap voltage, as well as it will make the circuit sensitive to VDD, because as VDD increases, the VDS of M1 and M2 will change in different ways. Okay. So, as usual, the way to combat this is to use cascode current mirror. Okay. That is, you make M1 and M2 instead of simple transistors, cascodes. That is one possibility. Another possibility is that this supply voltage here is regulated. Okay. That is, you make sure that this voltage does not vary too much. Now, this does not have to be very tightly regulated, because this already rejects the effects of power supply to some extent, because from the ideal analysis, the output voltage is independent of everything. It is when you put the channel length modulation effects in the current mirror M1 and M2 that you see some effects. Okay. So, it already rejects the effects of supply variation to some extent. So, even if that VDD BG, which is the supply for this cell, is crudely regulated, that should be good enough. So, both techniques are used. Sometimes you use cascode, sometimes you use the regulation, and of course, you can use the combination if you wish. Okay. So, this would be made cascode. So, these are the two ways of reducing power supply sensitivity. Okay. Now, finally, if you make the band gap reference and measure its output voltage versus temperature, you will see something like this. So, maybe this would be in the desired range of temperature. So, somewhere it will have 0 temperature coefficient and it will have a curvature of this sort. Okay. Now, just like we added the positive and negative temperature coefficients proportional to absolute temperature voltage and the base emitter voltage, we can also try and correct the curvature of this temperature dependence. Okay. For that, you will generate currents which have the opposite kind of temperature dependence by using appropriate combination of PTAT currents and constant currents and perhaps temperature coefficients of resistors. And if you add to this a small voltage which has the opposite temperature coefficient, then the resulting voltage would be more constant. Okay. Now, it will have some curvature which can be further corrected and so on. Okay. So, for reducing variations with temperature even further, one would use a what is known as curvature compensation. If you go through the literature, you will see a number of papers entitled curvature corrected band gap circuits and so on. So, if you see, sometimes they have a curvature correction of first order or even second order to get the output voltage to be as precise as possible over temperature. Okay. So, that concludes our discussion on band gap references. They are extremely widely used and they provide references for voltage regulators, which is what we are going to discuss next. Now, what is a voltage regulator? It has some supply and it is required to supply a constant voltage V out in spite of variations in VDD. Okay. This you would have seen very often if you have built some sort of circuit, then you would get the DC source from somewhere, but you will further regulate it using a voltage regulator. First of all, to get the voltage to the level that you want, and also minimize any variations in the voltage that you are supplying to your circuit. Okay. Now, this will need a reference because this by itself will not be able to hold the voltage accurately. So, it will usually use the band gap reference, which we have already discussed. Okay. And it will be connected to a load which I will model using a current source IL. Okay. Now, the current flowing through the supply now will naturally be the current flowing out, which is IL plus some current that is consumed in the circuit. I will call it IQ, the quiescent current in the voltage regulator, and also the output voltage is V out. So, the power that is driven out, power that is delivered to the load is V out times the load current, and power that is drawn from the supply voltage VDD is VDD times IL plus IQ. Okay. So, the power efficiency eta P out by P in equals V out by VDD times IL by IL plus IQ, which can be further written as this difference between V out and VDD, that is considered the drop across the regulator, that is from the input to the output of the regulator. I will call it V drop, and that is okay. Now, clearly to maximize the efficiency of the circuit, you have to minimize the value of V dropped and minimize the value of IQ, that is you minimize the drop across the voltage regulator as well as you minimize the quiescent current drawn from the regulator circuitry. Okay. Now, sometimes of course, the input voltage VDD and the output voltage of the regulator are specified. In this case, you have no choice but to take whatever V drop you have, and the efficiency will be in the best case V out divided by VDD. Okay. But in those cases where you have the choice of the input voltage or the output voltage, you minimize the drop so that you get the maximum efficiency that is possible. Okay. This is pretty obvious. Now, the voltage regulator, it is supposed to provide a constant voltage output with a very low output resistance. Okay. Essentially, it is a voltage controlled voltage source. Its input is the reference voltage and the output is the output voltage, which appears at a port which has a very low output resistance. So, now we have already made many amplifiers which has a low output resistance in feedback. Okay. Feedback is one of the ways, shunt feedback is the way to get low output resistance. Now, there are certain characteristics of the voltage regulator that make it different from a regular amplifier. Okay. It is basically a feedback controlled voltage source with a low output resistance, and it basically will be some scaled version of the band gap voltage. Okay. Essentially, it is like taking the band gap voltage and putting it through some amplifier K and getting the output voltage. But there are some particular characteristics of the voltage regulator. One of the things is that the low dropout means the swing limit of this amplifier, the upper swing limit must be close to the supply voltage VDD, and also normally you are required to support a load current which is more than 0. That is, normally this is powering some circuit that is drawing power, drawing current. So, you are only required to be able to support a current in this direction. Okay. You do not need to make this regulator work for a negative current unless you are talking about some special circumstances. Okay. And there are some other desirable features of a voltage regulator. We have already talked about a low dropout if possible. Now, this is for a few different reasons. Okay. Let us say your output voltage is fixed, that is you would like to have an output voltage of 3.3 volts. Now, you would like to operate it from any voltage that is higher than 3.3 volts. Okay. We cannot really operate it from a lower voltage than 3.3 volts, but you would you need a higher voltage, but you would like that difference to be as small as possible, right. So, maybe you are operating it from a battery and you would like the regulator to work even when the battery has drained out quite a lot, okay, so that its voltage has reduced. So, that is one of the reasons why you need a low dropout. Okay. Besides efficiency, you would like the regulator to be supplied with a voltage that is as widely variable as possible. Okay. Or put another way, if VDD is a given value, then sometimes you make a variable voltage regulator, that is V out is variable by some parameter of the circuit, and you would like the V out to have as much a range as possible. That means that V out should be able to go as close to VDD as possible. Okay. Now, the output voltage really should be absolutely constant, but in reality it will not. It will first of all change with the load current, and the fractional change of V out with the load current, which is basically the small signal output resistance of the regulator, must be small, and this parameter is called the load regulation. Okay. We are required to provide a regulated voltage, and load regulation talks about how well regulated it is in presence of variations in the load. And delta V out by delta VDD, this is known as line regulation, that is if VDD changes, the V out should not change. Okay. It should be whatever value we wanted it to be. That is one of the purposes of using the voltage regulator. So, you can take a voltage which is not well regulated, but provide a constant output voltage. This must be small, and this is referred to as line regulation. How well the output voltage is regulated against variations in the line voltage. And the output voltage must be accurately defined, that is another requirement. And finally, sometimes there is a step changes in the output current, that is the output current changes, and the transient of V out should be small as well. Here this parameter delta V out by delta I L, it talks about the steady state, that is let us say you change I L very slowly, how much does V out change, that is what the DC output resistance represents. Now sometimes the load current can jump, this can happen when you switch in a load or switch out a load, and then at that point the output voltage should not fluctuate considerably. Okay. So, in addition to this you also have this parameter V out of f by VDD of f. Okay. This refers to basically transfer function, of course for small signals, from VDD to V out. Naturally this number must be much smaller than 1. Okay. And the inverse of this basically this is referred to as 1 over PSRR, where PSRR refers to the power supply rejection ratio. So, earlier we talked about line regulation delta V out by delta VDD, and that again is a static parameter, that is for DC. The same thing is measured for higher frequencies, and that is called this power supply rejection, and this is also important. Even if you have high frequency variations on VDD, you would like to minimize them on the output line V out. Okay. And this can happen because of a variety of reasons. First of all, you have a number of circuits powered from the main supply. So, the main supply will have some variations which are related to currents drawn from that supply. Okay. Now, if you have a very sensitive circuit, especially some sensitive analog circuits like the oscillator, you would like to regulate its supply voltage. So, the oscillator supply should not have any variations ideally. So, you use a voltage regulator, and this parameter power supply rejection ratio characterizes how much variations you have in the output of the regulator for a given variation at the input at different frequencies. The parameter is of interest at different frequencies because circuits such as ring oscillators are sensitive to noise at some frequencies, that is some frequency noise matters more than the others. So, you would like to measure this power supply rejection at a wide variety of frequencies. Okay. So, first of all, if you need a low dropout, that is we have our supply line and we have the output line, and V out should be able to reach as close to VDD as possible. The best thing we can do is to have a single PMOS transistor between V out and VDD. Okay. Let me call this M0. Now, this PMOS transistor has to be driven in some way that the output will be maintained at the desired voltage. Okay. So, let us say V out happens to be, it is 2.4 volts and the reference is 1.2 volts from a band gap. So, you have to multiply this by 2 and provide the output. Okay. And the load current is drawn from the output voltage. So, what do you do? So, you want to generate 2.4 volts from 1.2 volts. So, you can divide the output voltage and compare it to the reference voltage 1.2 volts, okay. Integrate the difference and drive the gate of the PMOS transistor M naught, okay. And you go on changing the gate of the PMOS transistor until V out becomes exactly equal to 2.4 volts, or basically this feedback voltage becomes equal to 1.2 volts, okay. So, now the integration is implicit somewhere, basically the gate source capacitance of M naught will integrate the current that is coming out of this transconductor, okay. And if you look at the sense of feedback, you should have this to be plus and that to be minus. So, this is the basic voltage regulator, okay. In steady state, V out will be R 1 plus R 2 divided by R 2 times V ref, okay. So, this is fine, and also if you evaluate the small signal output resistance, let us say that you are operating with a certain load current, and let us assume that R 1 and R 2 are very large, okay. What matters is the ratio of R 1 by R 2 to define the output voltage. So, let us say that the current flowing through R 1 and R 2 is negligible, okay. This is just for simplicity. So, the transistor M naught will be operating with quiescent current which is equal to the load current, okay. And at that operating point it has a certain transconductance G M naught and a certain output resistance R D S naught, okay. So, what is the DC output resistance looking back into the circuit? I will not show it, but you can very easily analyze this circuit and see that it will be RDS 0 divided by 1 plus A naught, where A naught is the DC loop gain, and this corresponds to, let us say the DC gain of this amplifier is A1, okay. Let us say this has a transconductance of GM1 and an output resistance of R01. So, this A1 will be GM1 times R01, okay. And we have assumed R1 and R2 to be very large. So, the loop gain is the gain of this transconductor times the gain from this point to that point, okay. And the gain from here to there is simply GM 0 times RDS 0, okay. The transconductor has a gain of GM1 R01 and the transistor M0 has a gain which is GM0 times RDS 0 parallel R1 plus R2, and I have assumed that R1 plus R2 is much larger than RDS 0, okay. That will be GM0 times RDS 0. Now, we are usually justified in neglecting R1 plus R2 in comparison to RDS 0. That is because the regulator, when it is designed for very high currents, will have a very large MOSFET M naught and a very large current will be flowing through it. Now, if this is not the case, you can go back and put R1 plus R2 in all the calculations and qualitatively they will be similar, okay. So, the loop gain A naught is nothing but GM1 R01 GM0 RDS 0 times R1 by R2 by R1 plus R2, okay. And if this number is made very large, the output resistance will be small. So, it appears that this circuit will do the job by itself, but it is not enough. This is because one of the conditions was that if IL changes like a step, especially if it goes from a low value to a high value. Okay. When IL is at a very low value, the MOS transistor M0 will be operating with a small current. So, that means that it will have a high value of RDS 0 and a low value of GM 0. Now, when IL steps up to a high current, what happens is it takes some time for the gate voltage of the MOSFET M0 to change. That is because the gate of the MOSFET M0 has a large capacitance and it has to be charged from this transconductance GM1 to be able to change it. We also have this additional condition that the quiescent current dissipated in the circuit should be small. So, that means that the quiescent current used for this transconductor GM1 must be small. So, we cannot have a very fast response for this amplifier. So, it means that the moment that IL is stepped up to a high value, the output resistance does not change immediately, okay. That is, the feedback does not respond, and if you look at the output voltage, it will step down by a large value, okay. Basically, what I am pointing out here is that R out is made small using negative feedback, okay. So, if R out is very small, you would expect that if IL steps up by a large value, then the output voltage will be a small step, it will be equal to delta IL times R out. But because R out is made small using negative feedback and it takes some time for the negative feedback to respond, the moment IL changes, the output voltage will step by a large value and it will slowly settle down to the small value given by delta IL times R out, okay. This is what you would see. Let us say IL steps up from a small to a large value and the output voltage, let us say it is supposed to be here, and just after the step essentially it is still seeing the old value of R out, so to speak, and R1 plus R2, okay. So, it will step down by a large value, which if this is delta IL, this would be delta IL times RDS 0 parallel R1 plus R2, okay. And then the feedback kicks in, it will take some time, there will be slowing and settling of the feedback and finally it will settle down to the right value, okay. And after it settles down, the difference between the original and this one will be equal to delta IL times R out, which is rather small, but the transient voltage dip will be very large and this is clearly undesirable, okay. So, what is normally done is to have a large capacitor here, so what happens is in steady state this output capacitor C naught will be charged to the output voltage, and if you have a current step, the charge will be drawn from the capacitor, the current will be drawn from the capacitor and the output voltage does not change all that much, okay. How much it changes depends on the size of the capacitor, but by using a very large capacitor you can reduce the change. So, instead of having this large dip, what will happen is that the output voltage will start to reduce as a ramp and it will go on reducing until the feedback effects kicks in and it will do that, okay. So, roughly speaking, this is the time required for feedback to come into picture, and this is related to the inverse of the bandwidth of the amplifier, and after that it takes some time to settle, and that is related to the settling time of the feedback loop. Okay. So, it is very common to use an output capacitor which is very large along with the voltage regulator. Otherwise, the regulator will not be able to perform well when there are transients in the load current. Okay. Now, it turns out that introducing this capacitor introduces complications in the negative feedback system, okay, because as usual the negative feedback amplifier has to satisfy its stability criteria. Now, this large capacitor introduces some pole and possibly a 0, as we will see later, and we have to take into account these things while designing the overall amplifier, its bandwidth and so on. Okay. So, now we have to worry about stability of this negative feedback system. First of all, there is one large capacitor that is definitely going to be present, and that is the CGS of M0, and any parasitic capacitance at this node I have also absorbed into the CGS of M0. Okay. So, this will definitely be there. So, at least you will have 2 poles, but in general you may also have poles inside the transconductor, okay, and you will have some parasitic capacitance here, which along with R1 and R2 will make the loop gain have another pole. Okay. But the dominant ones will be at the gate of the transistor M0 and due to the output capacitor C0. The feedback resistive divider and so on. So, even ignoring this, we have at least 2 poles and we can analyze the response of this one. Okay. So, ignoring everything else, we will have we will consider only these 2. In reality, you also have to consider all other poles which you do by simulation usually, and let us say this has a transconductance of GM1 and an output resistance of RO1, okay, and this has a transconductance of GM0 and an output resistance of RDS0, okay, and we will continue to make the assumption that R1 plus R2 is much more than RDS0. Now, the value of RDS0 depends on the load current. Just for simplicity, I have assumed that for all values of load current, R1 plus R2 is much more than RDS0. This is just to simplify the expressions, but instead of RDS0, you can always put R1 plus R2 parallel RDS0 and you will get the more accurate result in case R1 plus R2 cannot be neglected like this. Okay. Now, what will be the loop gain function of this system? If you look at the function from A to B, okay, the transfer function from A to B, we will have GM0 times the impedance here, which is RDS0 parallel that one, okay, and because C0 is very large, the pole associated with this node is likely to be at a low frequency, okay, and that will tend to be the dominant pole of the system. So, from A to B we will have a response like this with a DC gain GM 0 times RDS 0 and the pole will be at 1 over RDS 0 times C 0. Okay. And it will roll off at 20 dB per decade. This is the transfer function from A to B, and the DC value would be GM 0 RDS 0. By the way, earlier in the course we have analyzed the frequency response of many of these things in great detail, okay, by writing out the expressions and so on. I am assuming that you are already familiar with that. If not, please go back and review those things. So, here I will not go into detailed calculations, I will write down things by inspection. If you have sufficient experience with this kind of analysis, you will also be able to do the same. Okay. Otherwise, you can write down the expressions and make sure that they are consistent with what I am writing over here. Okay. This is the transfer function from A to B through the transistor M0, and if you look at from B back to A through this voltage divider GM1 and this output resistance and this capacitance, we will have another low pass function. Okay. And the DC gain of that will be GM1 RO1 times the voltage divider ratio R2 by R1 plus R2, and the pole associated with this node, it has this capacitance CGS 0 and this resistance RO1 in parallel. Okay. So, this will be at CGS 0 RO1. Okay. So, the overall response would have a DC gain, that is product of the two DC gains. It will have a pole here and another pole there and do that. Okay. This is P1 and let me call this P2. This will be the DC loop gain. Now, clearly for stability we would like to have this P2 far enough away, so that when the loop gain magnitude crosses unity we have a roll off at minus 20 dB per decade. Okay. This we know from stability analysis. So, the constraint is that the pole P1 must be at a sufficiently high frequency, so that at the unity loop gain frequency we have a 20 dB per decade slope, or in other words we have a sufficient phase margin. Okay. Right now the way I have drawn the magnitude plot, this is not the case. So, this means that P2 has to be pushed out further. And P2 is 1 over CGS 0 times RO1, and this has to be greater than omega u loop, which if it is designed well we would have a single pole type of response and P2 somewhere over there, and this omega u loop will be approximately A naught times P1, where this is P1 and that is A naught. Okay. And A naught we know is GM1 RO1, GM0 RDS 0, R2 by R1 plus R2, the DC loop gain times P1, which is 1 over RDS 0 C 0. Okay. This is the constraint. Now, the MOS transistor M0 is designed for carrying a certain load current. So, that means that it will be a very large device. So, that will have a given CGS. So, from this expression we will get a constraint for the output resistance of the amplifier stage RO1, which translates to a limiting on the DC gain, okay, and this limits the line regulation. We will discuss these issues further in the next class. Thank you.